Hello, and welcome to the last of the lectures for Chapter 1. This will tie off Monday of the second week for class, and we're going to cover boiling points, melting points, and just sort of tie everything together. I hope this one is significantly quicker than the last two I put up for you. So, of course, you can just look at the time at the bottom and know how long it is, but I know how long it'll take at the time I said that. So we'll see. Let's go. So, boiling points. Boiling point, its highest temperature at which a liquid may still be present. That's kind of our common sense observation. So if something's a liquid, must be at or below its boiling point, but above its melting point. But the more correct term that you probably used when you took GChem, it's the temperature at which the vapor pressure exerted by the molecules evaporating from the surface of the liquid, equals the atmospheric pressure, the pressure pushing back down. I'm not going to go through that definition. I'm going to stick with this one, highest temperature at which a liquid may still be present, because it's more of a pragmatic or practical definition that we need for OChem. So highest temperature at which a liquid may still be present is our boiling point. Note that it varies with atmospheric pressure. We're not going to worry about that in this class. That's a GChem topic. That's a physics topic. In organic chemistry, you're interested in the reason behind that value. So, of course, I'm just sitting here reading to you, which you could just do on your own. So I avoid doing that. But I want to reiterate something from last time, and that is the two factors that play the biggest role are, number one, how heavy the molecule is. Heavier molecules take more energy to lift, to pull out of the liquid that they're in and let them evaporate and go into free motion in the gas phase on their own. And then intermolecular forces. The stronger the forces holding it in solution, the harder it's going to be to evaporate and the higher the boiling point. So the boiling point basically is a way to estimate the intermolecular forces, but not perfectly, because we still have to worry about mass. So if I want to compare two molecules of comparable mass, then the difference in boiling point is going to be based on intermolecular forces. Two molecules of roughly equal intermolecular forces, then mass is going to be the difference. So you have to take both of them into account. So acetone's been very popular. I brought this up a lot. So last lecture we mentioned boiling points in 56 range. I'm going to add something called ethanol, very common compound. And I picked these because they're kind of close in boiling point, and their mass is slightly different. So let me see what the mass is exactly. This has 1, 2, 3 carbons in an O. This has 1, 2 carbons in an O. 6 H's, 1, 2, 3, 4, 5, 6 H's. So H's cancel out, has an O, but ethanol has one less carbon. So if it was just based on mass, we'd expect acetone to have the higher boiling point. However, this compound, ethanol, has an H bonded to an O, so you know it can form H bonds, whereas acetone, all the H's are on carbon, so it cannot form H bonds. So by virtue of having H bonds, ethanol has greater intermolecular forces. So I have this contradictory question going on here. The heavier molecule should have a higher boiling point, but the one with higher intermolecular forces should have the higher boiling point. So I have to actually see the numbers, and then from the numbers, make a conclusion. So molecular mass 58.1, boiling point 56, molecular mass around 46.1. So again, one less carbon, as we mentioned, same number of H's, same number of O's, but one less carbon. Carbon has mass at 12, so not a surprise. Boiling point around 56. This one's around 78. So notice then, in this case, the drop in mass, although at face value would assume the lower boiling point, the intermolecular force increased due to hydrogen bonding, raises the boiling point substantially. So in this particular case, we can say the intermolecular force factor was more significant than the mass. Okay, perfect test question. Not that that's a hint. I just toss that out there. Okay, so continuing on boiling points, I want to again reiterate how these structures are being drawn. So we haven't formally gone over these, but I've seen them a couple of times so far, so I'm going to get a little bit more familiar with them. This represents a carbon, the endpoint here, a carbon and a carbon. So let me draw this as a carbon, bonded to a carbon, bonded to a carbon with a double bond to O and an OH. And you just fill in the extra H's. So this, to make 4 bonds, would have H there. So we've come so far, we just assume the honk rule is something you just automatically know. So this is how you've been drawing it as a Lewis structure, but we're going to try to go in this sense. So let me go ahead and see what's true about these compounds without drawing everything out. Here, 1, 2, 3 carbons. This one I'm sorry, 1, 2, 3, 4 carbons. 4 carbons, 1 O. I apologize. The structure I put up there when I first drew it should have had a CH3, not an OH. So let me go ahead and redraw that. And that's the difference between me doing them here and in class. Is in class, you'd be able to correct me. And as I'm doing this, I will confess that in class, I'm going to make mistakes, some on purpose, some unintentional like that. Definitely bring it up as part of the whole learning process. Recognizing mistakes and learning from them is key. Learn from your own mistakes, but also learn when I make mistakes as well. So not that it was that significant as far as the mass goes, an OH compared to a CH3 is hardly any change in mass, but a substantial difference in terms of an OH here compared to no OH there. Okay, so here I have 4 carbons, here I have 3 carbons, here I have 2 carbons, no OH, no OH, no OH. So again, let me erase everything now and just get back to what the whole point of this was. The point here was 1, 2, 3, 4 carbons, 1 O, 1, 2, 3 carbons, 1 O, and 1, 2 carbons, 1 O. They're all 3 carbonyls. This is what's known as a ketone, but a double bond to O with no hydrogen bonding. Double bond to O, no hydrogen bonding. Double bond to O, no hydrogen bonding. So their intermolecular forces should be very similar. Their polarity, because of this bond, should be very similar. So their intermolecular forces, no H bonding, and roughly comparable polarity means the difference in their boiling points has to be focused on molecular mass. So 4 carbons is heavier than 3, 3 is heavier than 2. So sure enough, this one's the largest, middle, and smallest. Okay, so molecular weight matters. So I'll put a little note, molecular weight is the defining factor there. Okay, so this example, this is 1, 2, 3, 4, 5 carbons in an OH. This is 1, 2, 3, 4, 5 carbons in an OH. And this is 1, 2, 3, 4, 5 carbons in an OH. All 3 have hydrogen bonding. All 3 have 5 carbons. So they have the exact same molecular weight. They have the exact same functional group. So my first guess at this point is same boiling point, same molecular forces, because they all have hydrogen bonding, should have the same boiling point. This is where my thought process is a little too primitive. Their boiling points are close, but they are not exactly the same. So how the heck did that happen? So I predicted molecular weight being greater for the first one than the second, third for this first example. No problem. Fit, I could have predicted that. This one, same molecular weight, same functional group, so same H bonding. So somehow, some way, where the OH is located is clearly playing a role. And the reason it plays a role is if it's all the way at the end, it's going to be easier to get to. It's going to be easier for that to find another O to form an H bond with. When it's in the middle, like here and here, and this isn't perfectly in the middle, but it's internal, if you will. This I'm going to call terminal. This is internal. Internal and internal, they have 2 carbon-rich groups, which are large, which prevent it from finding another alcohol, finding another partner to bond with. So these 2 are really close. And any difference between these 2 really comes down to this 1 carbon is a little bit smaller than 2 carbons. And then 2 and 3, anytime you go beyond 2 and get longer, it really doesn't matter. This is so far down, it doesn't interfere, but this group does. This one, it can't swing around and interfere, whereas this one can swing down and interfere. So just a little bit more interference, so this one won't interact. That interference is going to be something called steric hindrance. So when it's terminal, it can get close to other alcohols and form a stronger interaction. When it's internal, it can't do that. That's going to become a kind of key point we start getting into later chapters. So terminal can have stronger intermolecular forces, stronger H bonding. Internal, not as strong. So the boiling point is higher because of intermolecular forces. So here I was thinking I just had to compare hydrogen bonding to polarity to London forces or London dispersion forces. And I was real happy because that was simple, or molecular weight is all I had to consider. But within the interactions, I also have to take into account how close 2 molecules can get to one another. Okay, so that's kind of a tricky one. I feel kind of proud that I threw that at you. So now let's see what's going on in this example. So this looks awfully similar to what we just did. Terminal, internal, terminal, terminal, but it also has molecular weight. So lots going on here. So 3 carbons and terminal, it's at the end. 3 carbons, but internal. 2 carbons, terminal. And 1 carbon, it's redundant to say terminal because you really just, with 2 and 1, it was kind of silly for me to put that there because you're either one end or the other end. There is no end, there's just 1 point. So from what I learned before, 3 carbons and 3 carbons, they have the same mass. They each have an OH, so they both have hydrogen bonding, but terminal can get closer than internal. So I predict this one is going to be slightly higher than this one. And then 3 carbons weighs more than 2, 2 carbons weigh more than 1. So I'm going to predict this boiling point to be slightly higher than this, which is slightly higher than this. So earlier example, we said this one was 78. So one of the things I want you to get in the habit of doing is try to stay ahead of the lecture, figure out what I'm going to do next. So I'm going to say this one is maybe around 50, and I'm guessing. Not going to tell you why I guessed 50, other than it's less than 78, and it seems like a decent amount. It might end up being 64, it might end up being 68, might end up being 49. I don't know, but I know it's less. This one's longer, so I'm going to predict it's going to be more. So I'm going to make this one maybe around 100, and this one maybe around 110, because I know last time it was closer to 15, 20 degrees difference between terminal and internal. So I might be off on that. So this is strictly a guess. And it doesn't matter how close I am as long as I have them sequenced the right way. So most of the questions you're going to get in this class, rank which boiling point is higher. So I'm going to do this. And I was way off on the boiling points as far as the exact values go, but I was right on the trend, and that's what matters. So I'm going to correct it and realize, okay, increase the number of carbons, only raised it around 20, and only lowered it around 15-ish. And then it was raised, let's say 20 by being heavier, but then we lost about 10, 15 of that because terminal versus internal. So it only ended up being around 4 to 5 larger than this one. Okay, I feel good about this. And what you should notice is I was off on my guessing. I'm in the ballpark in terms of trend, but I'm off in terms of numbers. So is that okay? You bet. This is about learning the concepts and learning what things matter. And then you can always look up numbers to get exact values. So yeah, I was off. I don't care that much as long as I know this was highest, second, third, and fourth. Okay, so a couple here. Let's see, 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. So they're all 5 carbons. They're all in OH, but they're all in this case terminal, terminal, and terminal. They're at the end of the chain. It's dangling off the end. So their boiling points, I'm going to predict, are really, really close. But now it introduces that whole concept of steric hindrance. This extra methyl group closer, this carbon dangling off the side, can interfere, maybe interfere, and then it's way over here, so probably not interfere much at all. And so what I learned was if it interferes, it's going to make the boiling point go down. So this one, let's say, we'll take as our baseline for before. This one's going to be, I'm guessing, a hair less, but not much. So terminal versus internal, that was significant. That's 15 degrees or so. When it's still terminal, 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 but you move this group over, we got to figure out what we're going to guess. So I'm going to guess maybe 5, 10 degrees difference. We'll see in the boiling point. So 138 to 131, 7-degree difference. And when it gets closer, just a 2-degree difference. Nomenclature, just a heads up, for nomenclature, it's all going to be learned by video. We're not going to actually, either me or Professor Santos are not going to go over nomenclature in class, but there'll be videos up on it. And more importantly, office hours and questions, but it's one of those things that you sort of learn by doing. It's a pure memorization scenario. And so we'll bring it up every chance we get. So I should do this and say meth is 1 carbon with an alcohol, so methanol. Eth is 2 carbons, O. And then OH on the first carbon, 1 propanol. OH on the second carbon, 2 propanol. Prop means 3 carbons long. Pentanol, 1, 2, 3, 4, 5 carbons long. So pent meaning 5. 1 meaning it's on the terminal end. 1 butanol. 1 butanol means the longest chain is 1, 2, 3, 4 carbons with an OH at 1. 4 carbons with OH at 1. Here's the first carbon. Here's my second carbon. So that's why we called it 2-methyl. 1 carbon, 2 carbon, 3 carbons. This is my carbon. That's why I call it 3, because it's on the third carbon. Okay, but the boiling point's really, really close. So this is what's known as branching. And the impact of branching is to make it harder for things to pack together. So the more branching you have, the more it's going to reduce the intermolecular forces, the more it's going to reduce boiling point, melting point, and so forth. Okay, feeling pretty good about this. So let's look at melting points. Melting points, it's how molecules pack together. The difference is between boiling point and melting point. In a melting point, you're taking molecules that are near each other, and they're going to stay in contact near each other, just they're going to be able to start moving away from each other. So in essence, you're just weakening intermolecular forces, not breaking them. For boiling point, you have to actually completely break the molecules apart from one another. So highest temperature at which a solid may still be present. And that's how I'm going to define melting point. Again, that is not the formal definition, but that's going to be our practical OCHEM definition. That's going to be our perspective more than definition. So intermolecular forces play a role. There's so many other things. So packing is going to be the biggest thing. So packing is how well molecules can come together. So tighter packing, I think when you push things together really tightly, stays more like a solid. If they can move around and float around, more like a liquid. So in general, the tighter things packed together, the higher the melting point. So the example we love to toss is long chain fatty acids, and we do that because we study them so thoroughly in bio. So again, let me do my quick double check if this is a bio-related acid. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is a bioacid. Again, acids are built from acetyl-CoA, a 2-carbon fragment. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This was made by fatty acid biosynthesis. I isolated an OCHEM, I have this compound. So 45-degree melting point, meaning it packs pretty tightly. If I make this one here, let me double check. It is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 carbons. So by having 14 carbons instead of just 12, it's going to be a little bit longer. It's still a bioacid. Molecular weight goes up by 2 carbons and 4 hydrogens. So notice it went up by 28. A little bit heavier, helps a little bit, but it's more the packing. The longer the chain, the more it can intertwine. Palmic acid, let me just double check. I'm going to cheat and say 240 to 268 means it went up by 28, so it went up by 2 more carbons. So I'm going to predict this is 16 carbons, and then we'll count to double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So far, so excellent. You can probably guess what this one is. Up by another 28. This is 18 carbons. And you'll notice, as molecular weight goes up, the boiling point went up drastically, but the melting point goes up 10, 8, 6. Really doesn't go up that much. So melting point, although yeah, it will increase with mass, it isn't really the mass that's making the difference as much as just the chain. Longer chains, the more can interact. So if you have 2 short strings, try to tie them together, they maybe don't tie very well, but the longer the strings, the more knots you can tie between them, the better they interact. Okay, time to take advantage of a little bit of bio knowledge you might have at this point. So I'm going to take one of these same acids and going to look at what happens when we start putting so-called double bonds or pi bonds into them. So stearic acid is one we're going to start with. That was the 18 carbon compound we had as the last example on the previous page. Oleic acid, this represents a bond right here. One of the things that we know about double bonds is they're formed when a pi bond goes like this. Well, it ends up that it forces this molecule. So the way I've drawn it here is kind of not really doing justice to it. I really should show it something like this, where it forces it to carry out this bend. You cannot rotate around a pi bond. If you try to rotate, you'll break this bond and it won't let it happen, which means this is locked in a bent formation. So if you think of how hard it would be to stack a bunch of individual strings compared to stacking something that's bent. Trying to stack things neatly that are bent, have them interact, gets much, much harder. I mean, if you think about stacking a bunch of strings compared to a bunch of pencils, you'll quickly figure out it is really, really hard to stack a bunch of pencils. They roll around because they're rigid. So because this has this rigid pi bond here, the molecules can't pack together very easily. And so therefore, the molecular forces go down, the melting point goes down. They aren't held as tightly. You perhaps learned this when you took bio, when they talked about the phospholipid bilayer and whether it was said to be saturated. And I'm going to add one little word here. So saturated, I'm going to say with hydrogens, or unsaturated, meaning it has a double bond. It doesn't have the maximum amount of H's it can have. So it's unsaturated with H's. If you have a saturated fat or an unsaturated fat, unsaturated means it has a double bond somewhere. Double bonds make them rigid. They don't pack as well. So if you have a cell membrane that it contains a lot of pi bonds in the fatty acid, it's going to not pack as well. That cell membrane is going to be a lot more fluid. So for instance, a muscle cell would want to have some of those pi bonds. But if you have no pi bonds, it's all sigma bonds, then they're going to knot together, tie very tightly with one another. It's going to form a strong interaction, making the melting point high, making that cell membrane very rigid. So for instance, bone cells would be filled with a lot of saturated fats. Fluid cells, like muscle cells, you would want to have unsaturated, more unsaturated so that they can have motility, they can change their shape. So interesting little random tidbit. The difference between a fish that grows up in a cold water environment and one that's raised in a warm water environment. In the cold water environment, because it's so cold, they'd have a tendency to freeze. Their cell membranes get rigid just from the water temperature. So they incorporate a lot more of these double bonds, these unsaturated fats into the cell membrane to lower the boiling point or melting point back down so their cell membranes don't freeze out. So that way they can continue their cell function. That's why if you eat cold water fish, you're going to get a lot more unsaturated fats. Whereas if you eat a lot of warm water fish, you'll get more of the saturated fats. So Arctic salmon, for whatever reason, are one of the healthier fish. This is one of those reasons. There's other things as well. By the way, today's lecture is sponsored by the Arctic Fisherman Society, Fisher Person Society. Okay. Moving on down the chain. This one has not one, but two double bonds. And I'm going to add in the word cis because they are on the same side. Cis and trans is going to end up being an issue down the road, but for now, just want to introduce that term. They are on the same side, so we call them cis. Trans is when they have to trans across. So when you have two double bonds, that makes it even harder to pack. Melting point's even lower. This would even make the cell membrane more fluid. And then linoleic acid, you have three pi bonds, all cis, which would result in an extremely low melting point or extremely fluid cell membrane. So they're all roughly the same mass. This is lighter by 2, by 4, and by 6. That's such a trivial amount, as we learned earlier, that it really doesn't affect the melting point much. But the cis and trans double bonds, so in this case, cis double bonds 1, 2, and 3 will make a massive difference in the melting point. So this ended up being part bio, part OChem. This is what I'm hoping you get out of this class, is that OChem is a foundation for explaining a lot of the things you learn in biology. And to some extent, it ties in with chem and physics, but bio is really where it has its most obvious connection. So again, they all have roughly the same mass, but different degrees of unsaturation. 1 pi bond, 2 pi bond, 3 pi bonds. The more pi bonds, the lower the melting point. Okay. So the type of unsaturation, mentioned it, also makes a difference. This we said was cis because these two are on the same side. This one up here, we're going to call trans because they are on the opposite side. It ends up, as I drew before, that when you have cis, it forces to bend in a certain way, whereas trans, you can still keep propagating in a linear-like fashion. So trans can stack together better than cis. Cis messes things up. So trans, the boiling point, or excuse me, melting point is still lower than what we had before. So I think it was 69 degrees was the one without a pi bond. So still adding a pi bond, preventing the rotation, does lower the melting point, but much more when it's cis. So cis pi bonds have a much more impactful interaction or impactful impact. That's a terrible sentence, but they impact the melting point much more than trans. And so again, stearic acid, like we mentioned, was 60 something, so 69 degrees. A trans double bond brought it down by roughly 24, whereas a cis double bond brought it down by 56 degrees. So pretty significant. So this is going to be a solid at room temperature, solid at room temperature. Cis is actually a liquid at room temperature. This is a healthier fat for consumption. So melting point goes down significantly more when it's a cis double bond than it does with a trans double bond. Okay, so one last cell bio spoiler alert. So this is kind of a, I don't know, recurrence of what we had earlier, but I just want to go into a little more detail. And that is the packing of lipids in the phospholipid bilayer obeys the same rules as the packing of lipids in the solid. The same things that make the melting point lower will make the cell membrane more fluid. The same things that make the melting point higher, tighter packing, make the cell membrane less fluid. So here's my cell membrane. I tried to draw it a little bit different than last time. Not a perfect drawing, it's kind of ugly in its own special way, but again, keep in mind, cells surrounded by water, has water in its core, and then the phospholipid bilayer. So here's your phospho head, the positive charge or negative charge, depending on what it is. I'm going to assume it's all negative, phosphate. There's a phosphate here as well. And then lipid bilayer that kicks in. So hopefully it seems okay. These are your two alkyl tails. This represents the phosphate head. So if all lipids are saturated, it's going to pack really tightly and be more rigid. If all of them are unsaturated, it packs loosely and going to be more fluid. So again, pi bonds, unsaturated, melting point goes down, cell fluidity goes up. That's a connection. So you are learning your cell bio and your OChem simultaneously. Exact same reasoning behind both. And I hope in that if you eventually take cell bio, this will suddenly make more sense when we talk about cell membrane fluidity. Or if you've already taken cell bio, you already know this, and this will make the melting point easier. You got to learn it first, whichever class you take first. But this is why OChem ties so well into it. So that covers it. That covers this chapter. This chapter was hopefully a significant amount of review for you. You got it from GChem, got a little bit from bio, cool applications. It goes fast for the amount of information we covered. Make sure you do the homework, take your time going over everything, get this foundation down pat, and realize that by the time we're 2 weeks from now, this is going to be so old news and automatic from all your repetition that you won't stress about it anymore. But stress about it today so you don't worry about it tomorrow. So that's it. Have an absolutely wonderful study time, and we'll see you at the next lecture.